A fascinating proof of Euler's famous formula without using Taylor series. The core theme of our proof is that exponential functions and sinusoids have the same interesting property. Whenever you differentiate them, they keep the same functional form. And so, let's say y is cosine theta plus I sine theta, and take the derivative with respect to theta. This would be negative sine theta plus I cosine theta. And now let's represent the negative in front of the sine theta as I squared. This allows us to factor out an I, and if we look at the inside of the brackets, this is nothing but y cosine theta plus I sine theta. This gives us a differential equation to solve in y. We'll separate the variables, integrate both sides. The integral of 1 over y is the natural log of the absolute value of y, and the integral of I d theta is just I theta. But this is an indefinite integral. Let's not forget to add a constant of integration. Now, to solve for y, we'll exponentiate both sides. This cancels the log on the left. And we'll use laws of indices to represent the exponential as e to the I theta times e to the c. And now, to undo the absolute value around the y, the absolute value is just the positive or negative version of that number, depending on what interval the number lies in. So, we have this plus minus e to the c, which is just one big constant that we can rename k. And now, to find this k, we have to use an initial condition. The easiest is 0. So, when theta is 0, what is y? Sine 0 is just 0, and cosine 0 is of course 1, and so we know that y has to be 1 when theta is 0. Let's invoke this initial condition. E to the 0 is just 1, and so k must be this y of 0, which we showed to be 1. And so y is e to the I theta. One thing I'm sure we can agree on is that y is equal to y. And so, there you have it.